All right, so let's get started. Hello, everyone. I'm Jinhua Zhao, Professor of Cities and Transportation Planning at MIT. Welcome to the MIT Mobility Forum, organized by the MIT Mobility Initiative. Today, we'll discuss the topic of the risk within the material supply chains for transportation. I'm really glad to have Professor Elsa Olivetti join us, share with us her work and research and practice in this area. Everybody knows that transportation is transforming drastically from the internal combustion engine to electric vehicles, right? So the EV and ICE require totally different mixtures of materials, right? Now we'll talk about cobalt, lithium, nickel, copper, graphite, a whole set of material that EV is demanding. So we really have to look at the whole supply chain from the mining, sourcing of the raw material, to the processing, to the battery grade material, to the manufacturing, to the cells, modules, packs, etc. Meeting this demand really have to be grounded in the mineral supply, not only in the environmental sense, but in the social economic sense, right? So really need a robust approach to evaluate the availability of this material, and particularly incorporating the economic feedback and structural understanding of how this supply chain will evolve, right? I'm really glad that Professor Elsa is agreed to join us and share with us her thinking on this, and particularly also then offer certain ideas and strategies for us to maintain and be resilient in this process there, right? Before I formally introduce Professor Elsa, I do want to do a quick poll to get a sense of who are in the audience here, right? So we'll start the poll. Question number one. It's a simple question about the level of engagement in the material discussion. Are you conducting research on material directly as a researcher? Or are you practicing in the industry and the government on material? Your practice is indirected, but related to material, or are you mostly just curious about it? There's 100 people participated so far. I'll give a few more seconds. All right, so I will pause here and share the result. So about 7% are actually researchers on material science, 8% practicing it, 23% are indirectly related, and 60% about just curious, right? So hopefully that gives you a context on this, right? And next, I do want to invite everybody to type into the chat your organization, location, and time, right? Again, to give a sense of who's in the audience here in the chat. So I will do MIT, Cambridge, 12 of them. Thanks. Right. Yeah, while everyone is typing in your organization, location, time, let me introduce Professor Elsa Olivetti. She's the Jerry McPhee 1940 professor in engineering, professor of material science and engineering, McPhee's faculty fellow, also the associate dean of engineering at MIT. Her work focuses on improve the environmental and economic sustainability of materials. Specifically, Elsa develops the analytical and computational model to provide early stage information on the cost and environmental impact of a material. Professor Olivetti works towards improved sustainability through increased use of recycled and renewable material, recycling-friendly material design, and intelligent waste disposition. Professor Elsa's group also works on the understanding of the implications of the substitution, dematerialization, and waste mining on material market. She's a member of the MIT Climate Nucleus and a co-director of the MIT Climate and Sustainability Consortium. Also very relevant to today's discussion, Elsa actually contributed to the report on securing Americans' future. That's much of the sections on material security, so Elsa contributed to that, right? Before I pass the forum, I just say that reinforce the norm of this forum, which is ask every audience to contribute idea, either a question or a comment to Elsa's presentation directly in the chat. Without further ado, let me pass the forum to Elsa, please. Thanks.
Jinhua, what a wonderful opportunity. It's really an honor. This is an amazing community you've assembled. And in your kind of introductory commentary, when you were framing my talk, you said it all in a very eloquent, concise, pithy way. So it's really an honor to have an opportunity to appear on a Zoom screen with you. And thank you. I'm very eager and very excited for this discussion. I talk a lot about this topic. It's a topic I'm really passionate about, but thinking about it from the lens of this community, of the MIT's mobility initiative that's been such a strong force on campus for building intellectual community with this lens is really exciting for me. And I probably haven't done as sufficient a job as I would like. So I'm very eager for your comments and questions of kind of how do you see all these supply chains? And I think about, mines and materials. We'll talk about recycling. How do you think that they play out in the mobility space as that moves into the future, but also in an urban context? So I'm very eager for the dialogue. So I'm going to kind of frame the problem a little bit and how we think about it and our interests in the topic, and then very eager to have a dialogue with Jinhua and what this means for the context here. So I'm going to level set in ways that probably many messages you all have heard. This is a topic that's been on the press, day after day after day, but hopefully there's a couple new lenses here in the way that you think about it. And this work is part of an effort across many folks that I've worked with in the research group that I have, but also working with the Material Systems Lab at MIT, whose research director is Rich Roth, here listed in the middle of this set of 5 faces. And then my students, Drs. Jinhua and John Ryder and Basui Ravi and Karan Buwalka are obviously strong contributors and developers of the methods that I'll share some results around here. So first, to frame the overall question, we all know, we hear often in the literature and in the popular press about that the deployment of energy transition technologies really means we have an increase in the demand for materials in terms of quantity, but also the types of materials. And so to make that point, I really like this figure from the IEA that shares the amount of non-structural minerals that are relevant to incumbent technologies below the red line and the new technologies or low carbon technologies, so to speak, above the line for transportation and power generation. And really, you see above the line, there's the bars go further to the right in terms of quantity. So non-structural elements that have a broader range, both in the types and the quantities, are very resonant or very important and significant in our low carbon future. So it's going to be minerals intensive because clean energy technologies need this broader range, broader palette of materials. And so then that means we need an increasingly complex set of supply chains to meet that demand, in addition to lots of new efforts, both on the primary side, but also in secondary and recycling, as we may get to later on in the discussion. And so that's very focused on transportation and the power generation, but it's not just batteries for energy storage, which is what we tend to hear about a lot in my upper icon there. The need for new technologies across many areas in transportation are going to require more material and better materials to address current societal challenges. So I just have a couple of other examples, again, just to give you a sense of the tip. We're at the tip of the iceberg when we're talking about sort of relevance in battery materials, even though that's a really significant part of what we need to think about, right? We need to be thinking about electrofuels we're going to require new catalysts. We need to think about carbon capture that needs to think about new gas storage materials. Or if we're thinking about a hydrogen economy, there's a whole suite of materials there. And so this is increasingly leaning on material supply chains. And we need to think very thoughtfully about the broad implications of that. And then as Jinhua said, we think a lot about recycling and alloy design in my group. And even there, as we think about a broader palette of elements to make materials that are more lightweight, more durable, what does that do for their recyclability? So lots of reasons to feel urgency about the topic. And then, I think the demand side is clear. It's oft discussed, but I just like to frame it a little bit that, you can see in these plots shown on the right that for cobalt, nickel, copper, and lithium, the significant demand growth that we're expecting to see the historic growth here is, just these lines here, that was already dramatic, already exponential. But then when we think about the percentage increase relative to all these points I've made up to now, it is a significant challenge in terms of production, meeting those demands while not, facing significant unintended consequences. So that's about this sort of demand and the diversity. We also hear a lot about the geographic concentration and what that means. And often we hear about it in terms of the mining, where the mining is occurring. So the top producing countries in production of fossil fuel technologies listed here for natural gas and oil. We know the geographies reasonably well. When we start to think about minerals, it again becomes they're more concentrated in many cases, and that it's a different set of players. And so this is again the top producing countries for the production side across copper, nickel, cobalt, graphite, rare earth, lithium, and platinum. We see different kinds of concentrations, different sorts of geographic challenges. But it's also a geographic shift on the processing. And here, often we talk about the role of China in significant manufacturing, and that's really on the processing, sort of downstream a bit in the volume of these materials, where China is obviously, as the red plays out through this slide, the significant player, and obviously friend of mine in a lot of ways in which we think about policy design in this space. So the other thing I like to bring up when we think about the geography challenge here is really just how global and how extensive the journey is that the materials go from when they're mined. For example, I'm just going to walk you through the journey that a lithium molecule takes going from the mine in Chile here. And so I'm going to track it on the map on the upper left here, but then you can see on the supply chain on the bottom right, just to get a little sense of what the battery supply chain looks like for these materials. So first we're extracting raw materials, in this case lithium. So in the middle of my supply chain diagram here, and then we're going to go 5,000 miles from Chile to Alabama to be refined into battery grade lithium carbonate. So then we're proceeding down my supply chain to material processing. Then we're going to go from Alabama we're to LA and then to Japan as we're going to do some further refinement, the other half of material processing. And then we're going to go to Shanghai, where we're going to take that precursor material, as it's called, and now mix it into a slurry that's going to go into a constituent for a cell, so making an electrode of a battery. And then we're going to make multiple trips within China to go not only to make the cathode and the electrolytes and the anode, as is shown in my diagram here, but also then to manufacture a cell. So all of these different parts of the chain. And then we need to go assemble the battery pack. We're going back to Los Angeles in this case for the battery pack assembly before we think about the end use. So just to give you a little bit of a snapshot, of the journey that each of these constituents is going to take. So here now I've framed, the overall kind of place-based journey that these materials take. And the challenge of this increase in demand, we can see is flagged by the geographic concentration, but also, as Professor Jinhua said in the beginning, there's a significant environmental impact associated with this extraction. And I'm going to just share a couple of different metrics and lenses that we use to think about that. So I'm showing here the tons of CO2 per ton of metal content for a set of materials, where I've broken it down by the processing and the mining of those materials. And we can see for things like iron and steel, that are more typical, we think about in terms of high volume materials, as we start to go to rare earths and nickel in particular, the impact is much greater. And that I'm going to come back to this point if we get to it in questions, but this is the impact now for the amount of material that we're using in nickel. But as we need more and we're looking at alternative processes, the CO2 footprint goes up to a factor of 10 in terms of alternative extraction processes. So the impact is intensifying environmentally. And then we know there's lots of social pressures. There was just an article in a paper earlier today about a project in lithium where there's been a suit brought against it. And there's significant challenges in permitting and the role that, or the impact that mining has on indigenous communities. So here I'm showing U.S. mines with critical materials reserves associated with native and tribal lands. But it's not just CO2, it's not just greenhouse gas emissions, it's also impact on water, and the juxtaposition of copper and lithium mines in particularly water-stressed regions, as is shown here. Water's maybe less of a challenge in other sorts of metals that we'd be considering, but there's an increase in waste generation from copper and nickel mining as ore grade is declining. And so here I'm showing the mined output on the left-hand side going down over time as compared to the tailings, the waste streams going up over time, as is shown on the right, and the challenge of that. And a lot of this has to do with the various stages and losses that are happened from the original volume of material that's extracted, for example, in cobalt here, and then what we're losing to tailings and slag in the mining, but then what's not being recovered in recycling. So losses that are happening all along the life cycle stage. So the kind of punchline here, before I hear from you guys of what the challenges that you face are, is that the low carbon future, as I said, is minerals intensive. We have ore grades going down, increased environmental pressures, but then the challenge that the industry faces is we have this mismatch in the amount of time it takes to build and develop and set up a mine. Here I'm showing lead time in years for mining projects. So our ability to be responsive on the supply side, juxtaposed with the challenge and uncertainty associated with demand. How many electric vehicles are going to be bought, but then in addition, what are the batteries that are within those vehicles? And so the mismatch and the challenge of the mining and refining industry meeting the demand of the transportation OEMs and manufacturing supply chains means that it's very difficult to be responsive in an environmentally and socially thoughtful way. And so that's the kind of punchline that I want to leave you all with, as we pose this sort of first question in the poll of kind of why do you care about materials availability, either coming into this discussion or based on how I framed it so far, which of these sorts of elements are play into your interests in the topic.
Great. I just launched it. I see 40 people already participated. I will give it a few more seconds for let's go.
Excellent. Yeah, you tell me what you expect in terms of.
Sure. Yeah, give me a few more seconds. Now, 90%, 90 people participated. Maybe a few more seconds. I was okay. So I think 95 is pretty good. I was and share the result. Right. Elsa, can you see the result there?
Yes. Yeah.
Great. Yeah. So supply chain concern, 29%. Writing policy, 5%.
Excellent.
Corporate strategy, 7%, environmental impact, 45%, general knowledge, 11%. Right.
Wonderful.
Yeah. So if you have other reasons, again, please type into the chat as a comment or question, and we'll prompt you.
Yes, that's great. Yeah. So a lot of interest in the supply chain concerns, and I'll speak to that now, and then environmental impacts that we mentioned some of, and we can come back to as well. Let me just make sure yeah. Oh, good. So thank you very much for that. I look forward to hearing more from the chat. The reason why we particularly have spent time thinking about the links between supply and demand, that mismatch that I just mentioned, is because the practical limits that price plays on energy technology scaling is going to be impacted by materials cost. And so then this mismatch that I mentioned between the ability for miners to provide supply relative to the uncertain demand, that's mitigated by economics, right? The economics of how much, what's our willingness to pay and at what price more supply will come online. And it's that trade-off that plays a significant role. And so that's why we care about materials price. I mean, for all the reasons you all mentioned, but why we feel it's important to look at it analytically to understand what might mitigating strategies be in terms of addressing materials availability risk. And so here what I'm showing is the kind of rationale the evidence of that is that as we are getting better at our various technologies in terms of the learning rate, so this is showing battery pack price over time, we start to hit a floor around not anything that's non-materials cost. And this bar chart is showing that as well, that within a battery, the full battery that I was showing before, the materials associated with the cathode and anode, with the electrolytes there, are a dominant source of cost. And so any kind of price volatility associated with those minerals, associated with what's happening at the mine, will start to have a pretty direct impact on the battery pack price. But it still takes a long time to build a mine, right? And so that sort of volatility is the challenge that's brought out here. And I just, share alongside that, that we see this volatility in cobalt and lithium and nickel and the battery relevant materials that is quite responsive. The battery materials, the active materials price, but it's difficult to be responsive to that in the supplying of those materials. So one of the main points I'd like to make sure I make is that when we talk about materials risk and materials availability, it's not about running out. That's not the primary concern that's not what drives this volatility. It has to do with the degrees, the inability to close that supply demand gap that I mentioned at the right temporal scale to otherwise we end up with these very cyclic, oscillatory behaviors, and the impacts of the efforts to close those supply-demand gaps. So the environmental implications of that, the social implications of that. And that's really this interplay between the market imperfections that might be inherent to a specific material, our ability to substitute functionally to other materials, how important to the particular technology is for this development, and then what the particular economics are for mines being able to move in this way in response to it. And so the one way to think about this in terms of the technology deployment, again linking this back to price, is price is this measure of the disruption and the supply risk associated with meeting this demand. And typically, at least in the academic literature, but also in the way the industry is informing its decisions, in some cases, there's incomplete capturing of this economic feedback. And Professor Junwan mentioned this at the beginning. So if we think about what that means, there's consumption and production tracking over time. And then if I'm saying that there's lags in the system's ability to respond as I'm having a growth in demand or consumption, and supply isn't keeping up, then there's some balance that's happening to fill that gap. And that balance might be taken up by increased production. But in addition to increased production from either secondary or primary sources, there might be lost consumption. And what that could mean is ways in which that hinders the ability to meet carbon goals, or doing and if that increased production is happening in ways that are not as environmentally or socially responsible as they need to be, then that's what the conundrum, the trade-off that we end up making at a more societal meta level as we try to decarbonize. And the ways in which consumption is responding to price, as I said, is reduced sales, is the so-called lost consumption, or substituting away from other materials or to other materials. And our ability to do that dynamically is the challenge. And then in terms of how production is going to respond to price, that's going to happen by mines opening and closing at these rates that I mentioned, on the order of 18-20 years, further resource exploration and recycling where it's relevant and temporally, and we can come back to that. So as I kind of close out these sort of opening framing comments on why these are challenges, and then we can dig into some of the materials in detail as you've interested. Oh, sorry, I forgot this. There's a recent work in looking at China's electric vehicle fleet, and found that these higher materials costs have led to upwards of 30% larger emissions from reduced EV deployment. So starting to really be able to think about that lost consumption wedge that I'm seeing there, and how do we mitigate that in ways that don't have an untoward, really significant environmental impacts. So kind of give you a sense of the complexity associated with this as I've talked through this. But many factors are at play, particularly when we think about the fact that we need, in order to meet demand, so anytime we have a growth in demand on the order of what we have now, requires primary metals extraction, right? There's more demand than there is supply currently that could be met through recycling. So that means there's going to be primary metals extraction. So it's going to be an essential element of battery materials and electrification. takes into account many different factors in terms of accelerating growth rates, the complexity of these supply chains that I've mentioned, the significance of this footprint of materials production generally to global emissions, upwards of 10 to 30%, depending on how you think about those sectors. Many of the processes associated with beneficiating materials are very difficult to decarbonize because of the inherent chemistry of those processes, or they are processes that are happening at high temperature. I mentioned the declining ore grades, which therefore is going to further increase the global, the emissions, the environmental emissions associated with that. In part because we, the more energy, we need to dig up more rock per metal content that we obtain, and also more exploration associated with that. The geographic concentration that we read a lot about in the news, and there's opportunities to think about that in terms of policy that would either be going towards enforcing best practices or very much more protectionist practices. And so we think about these things really very much the way the response to the poll reflected, right, of kind of grouped in this supply chain implications and this materials criticality linked to the environmental implications of that. And the other thing that's really very interesting in this space right now is all of the different ways in which governments are responding. And because of that journey that the lithium molecule takes that I shared with you, all of this legislation, this policy context ends up being relevant to how decisions are being made industrially by firms that are investing in these technologies. But then that has then an interplay back to how we think about it at a policy governmental level. So I'll just mention a couple here. Folks, obviously, I'm often very familiar with the Inflation Reduction Act, CHIPS and Science Act. And this is really an opportunity to think about this issue from these multiple dimensions, but lots of activity in Europe as well. European Action Plan on Critical Raw Materials and the Circular Economy Action Plan, and then activities in China. But then there's also national protectionist activities within Chile, the Democratic Republic of Congo, and then most recently, lots of activity from a policy perspective in Indonesia, where nickel is playing a particularly, where the attention has been around nickel extraction. And so not only do we need to think about the economic feedback, as I mentioned several times, between supply and demand, we also need to understand, how can we respond as a research community linked to the policy community as well. So I'm going to kind of wrap there, and would love to hear kind of which of these materials do you hear about in the popular press most, or which do you think is the highest risk of availability concerns based on kind of what we've talked about so far, and then we can use that to guide our discussion and also answer any other questions that you all have.
Yeah, that would be wonderful. Yeah. So I just launched the poll. So far, I think I also give a overall view of some of the general patterns of the materials, right? But the next part, I want to focus on like one specific, like a cobalt or lithium or nickel or copper. But for that, we like to gather people's preference of which one you want to talk about, then we will guide Elsa to that direction. Yeah. So far, 75% of people participate. I'll give you maybe 5 more seconds. Okay, so I will end the poll and share the result here. 35% on cobalt, 53% for lithium, 6% nickel, 4% copper, 1% graphite. Others, again, if you interested in others, please type into the chat which one particular one talk about here, right? So Elsa, do you want to pick one and give some more specific in the particular aspect?
Excellent. Yes, I definitely will. I think we'll go by the popular there. I'll talk a little bit more about lithium and cobalt, and actually it's quite interesting. We'll see where questions go, but there's a lot of interesting things to think about in terms of nickel, so we might share a little bit about nickel too. But first, let's talk about cobalt. So the cobalt is interesting to talk about for a couple different reasons. Sorry, I'm having multitasking problems. Did I do that right? Closing polls. Nope, that's the wrong screen. Hang on here. Sorry. There we go. Good. Okay. Sorry about that. So I'll just focus on some of the challenges that we hear in particular around cobalt. So the production is very focused on the Democratic Republic of Congo, and I'll go ahead and pull this chart up that we put together that talks about the resource flows in dollars, in millions of US dollars, and the thickness of the bar is that trade flow quantitatively. And we see that the sentence that I reflect there, that the vast majority of that is going from the DRC, but it's then being processed in China. And so there are significant social and political consequences of this extraction and kind of initially, maybe say 5 years ago, around the sorts of pressures that I was putting on the artisanal mining, or pressures because they were interested in the economic development angles of it in the artisanal community, mining communities within the DRC, as I'm sharing here. But now it's actually quite interesting because there has been such a tension and the industry has started to shift pretty significantly away from cobalt. At least in battery roadmaps, and there's a lot to unpack here around kind of anticipated demand and versus actual demand. Now the challenge I talk a lot to when I speak to the folks in the DRC government level is actually lost economic opportunity because there has been this shift. So it's kind of the worst of both worlds in terms of the environmental impact and devastation, but then that our attention switched so quickly, and even the kind of perceived anticipated demand that has a different kind of impact. The other thing that's particularly interesting and relevant in cobalt, that's another kind of metric we think about in terms of materials risk, materials availability, is the economics. And I mentioned this before, but cobalt is primarily mined as a byproduct. And what that means is that the mine is built for nickel or copper, and because of the value, dollars per ton. And it's that cobalt is a byproduct of that process. And what that means is that the price signals are not as sensitive, that as prices go up on cobalt, that isn't really perceived by the miners because they're getting their value from those middle colors on my little flowers there. And so that means that it's less elastic. There's more inelasticity to supply, which it has other kinds of delays in the system. So those are some of the challenges that are around cobalt in particular. And so the other popular, oh, please.
The other one, lithium.
Yes, excellent. So let's talk a little bit about lithium. We have to ignore copper there because copper was living on my lithium slide. So I'll just say briefly, just because it's there. Copper is actually one of my really passionate material that I care a lot about because it is ubiquitous, right? Kind of regardless of what we're talking about, if we're talking about low carbon technologies in electrification, copper is there, providing electricity, providing the materials linked to conduct. And so what that means is what they say here at the top, it's very challenging to substitute, but it actually had some of the most precipitous grade ore quality declines. And I made this point around water before in terms of where it is mined. So, and then the other thing that's quite interesting about copper, as different from cobalt, is copper is very high value and high volume. And so it means that it can be more responsive to things like recycling signals, for example. And so that's a material we've thought about a lot in terms of recycling. So lithium is quite interesting because it is required for most battery chemistries. So one thing that I didn't talk about in too much detail is when we talk about uncertainty in the battery chemistry, even within one kind of battery chemistry. So we often hear about nickel, manganese, cobalt batteries. Depending on how I'm thinking about each of those elements, there could be a factor of 4 different in the amount of cobalt, for example. But lithium is fairly constant as needed, and as needed is in up to a third of the cathode chemistry itself. And so that has a stability to demand to it that you don't see when I'm talking about that nickel cobalt schizophrenia that I just mentioned. But the other thing that's quite interesting about lithium is that it is extracted from diverse sources. Two primary ways we get it are from salt lakes, from brines, where we're evaporating, and that's a very energy intensive process to evaporate the water out of the brine, or we're mining it from rock. spodumene ore, it's called. And so that diversity in sources can also be helpful in terms of mitigating price volatility if there's multiple different ways, and those have there's different kinds of permitting challenges. And actually, the challenge from a supply chain perspective is downstream of lithium when we talk about the chemical processing of it and battery grade processing of that. When the batteries, because of this, it's required for most chemistries, batteries as a share of other uses for lithium has been growing pretty consistently in terms of the end use. And that's important because it means that we're more responsive to demand. If we talk a little bit about something like nickel, it's the nickel market in batteries is very small compared to stainless steel. And so again, that makes us less responsive to demand. So my kind of more higher level point on talking through a couple of these in details is that the details are important. These materials are not monoliths. I can't say materials availability is there's risk associated with materials supply chains and not talk about what supply chain am I talking about, because as I've mentioned, even in just talking through these three, the story and the context and the narrative of how they're mined, where they're mined, what else do we use those materials for, what are the downstream processes, how might we recover them at end of life, are critical to informing what the risks are associated with their availability.
Great. Oh, thank you, Elsa. So one thing, because many of the material, the demand, the increase really rather new, right? So therefore, for a while, the primary source will dominate. So by nature, recycling will lag behind on that, right? So I'd like to comment a little bit about recycling in several aspects. One is this delay of recycling. The second one is the complexity of that, right? So you take a battery, there's so much component, different product. From a recycling point of view, what are the basic understanding of recycling? Why is it so complicated? The third one is in your bio, you mentioned that you actually work on something called recycling friendly design, right? It's to say not to just take it for given, but instead from the upstream, when you design the battery, think about how you're going to recycle after the fact on this. But can we say a few words about the recycling?
Sure. Yes, it's a topic that I'm very passionate about. And you highlighted the kind of key challenge around recycling that I mentioned before is kind of when we're thinking about recycling in a growing market, recycling's role to meet supply in a growing market, it's very difficult for that to be a significant part of the pie, even in a perfect collection infrastructure, right? Even if things weren't so complicated. Here's just one way of framing that, that if we think about light and heavy duty electric vehicles placed on the global market over time, so here's the current and then projections out. So here's the axis you notice here in terms of tons of EVs, and then we then say, okay, well, how many of those batteries, based on the fact that it had to drive, that the car was being used and was driving around, or the truck was driving around, was reaching end of life. But I cheated by an order of magnitude here, right, on the scale bar. And so if I actually put the scales correct, you'll see that in 2030, then the quantity, the volume of material coming back is very small relative to the sales that are going to be happening. And so this, if we are electrifying at the rate we're trying to electrify our vehicle fleet, the ability for recycling to play a significant role is challenging. And here's just another way of slicing that by material, where I'm showing the demand and then the supply of recycled to be able to meet that demand. We say kind of 2040-ish timeframe. And so that doesn't mean we just sit back and say, oh, darn, we can't do any recycling. We have to be building the infrastructure now because of that complexity. And actually, as is true in many stories in manufacturing, where the capacity is being built is in China. And so if we think about global lithium ion battery recycling over time, where China is in gray and the rest and everybody else is in green, there's quite a discontinuity there between where the investments are going, and this is starting to shift. But because we the kind of policy attention span isn't, and because of the significant delays on the mining side, it's very difficult to have that be done. So you talked a little bit about complexity in your question. And there are many different elements of the complexity, and I'll just make 2 points. And this gets to the design, and I'll answer this question in a couple of different ways. So maybe I'll kind of answer those second and third parts together. So there's tons, what we always have, I have this joke, I say, what do we mean by battery? Because you have to think about, what's the chemistry? I've touched on that already. In terms of the amount of these materials that are required, but what's the shape of the cell that's being used? Is it a cylinder? Is it a prism? Is it a pouch cell? And then from there, so I've already got complexity at the chemistry level, I've got complexity at the form of the product level, but I've got complexity in how I'm putting it in the vehicle, how I'm doing the joining processes that are linking each of these cells to modules to packs. And there's no standard or labeling for battery cells, modules, or packs, or fasteners, or any of these things. So this gets to your question about complexity, but it also gets to the question around design. And in this case, design looks like standardizing across the, the cornucopia of manufacturers on the battery side, but also on the OEM side. Where there really needs to be concerted significant effort, and whose stage does that happen on, globally, to try to align these things, because we, even though mining is slow, mining is heavy, that is one system. And so if you're trying to at least until the processing starts. And so if we're already involving this many players just in taking the battery apart, that has a lot of challenge in terms of the complexity that is introduced. And then just briefly, there's also the process by which we would do the recycling, and what makes the most sense environmentally, economically, based on what context we're in and where the infrastructure has been invested. So this is a figure from ReCell, which is Argonne National Lab's effort in lithium battery recycling, just to show the different possibilities in terms of recycling, right? So here's battery use here. We could have that, we would have a second use in a non-mobile in a stationary application, or we could look at direct recycling, which would be lithiating the battery directly, lithiating the cathode directly to use it. We could process it chemically, we could process it thermally, and each of those approaches is going to have a different environmental and economic footprint that we want to be thinking about.
Great. Oh, thank you, Elsa. I have 3 or 4 additional questions, but let me pause here, give the forum to John to prompt some of the audience question. Please, John.
Thanks so much. Elsa, I cannot understate how much I love this talk, because it is so incredibly relevant. It captures the complexity of this sort of geopolitical, global supply chain, very almost overwhelming complexity of the situation, and really, really insightful stuff. And your talk generated an array of really thoughtful questions as well. I want to just jump right into them. And please feel free to offer very short answers, because we have many questions. So Saul Tannenbaum asks, are semiconductors a significant driver in the need for minerals, or are they just noise given the scale you're talking about here? So how do materials related to semiconductors versus automotive?
John, that's not fair. I can't answer that question briefly. And so it does show up on the radar for kind of different reasons. That's my short answer. And that has to do with the price premiums, right? It's a very different market. It's a very different way of thinking about what those are. So it is a significant, there's lots, we have a whole other kind of realm on the semiconductor side that I haven't talked about. And maybe, so silicon comes up in terms of an availability consideration, not the sort of palette that we have, but because of the difference in the economics there, it is important. So that's a quick answer.
Okay, let's go with that. Don McKenzie had a question. How do the near-term and long-term constraints on supply of critical materials affect the appropriate policy strategy for the transition to more electrified vehicles?
Yeah, this is a wonderful question. And I maybe meant to share the slide. I got too excited about my materials. But so maybe I'll just, what we see is, and I mentioned this at a high level, but that industrial strategy needs to include this kind of market feedback to think both about supply and demand at the same time. And so we need to think about so kind of the sets of policies that would inform supply, that would help reduce supply development timelines, but in thoughtful ways, engaging with communities. And we've done some work in best practices in order to do that, but it's about lowering the financial risks, streamlining permitting, and making sure that the pausing in the permitting process is happening for the right reasons because of community engagement, as opposed to it sitting on someone's desk, and making that as resilient to political shifts as possible. But doing that at the same time that technology innovation and policies are strengthening demand. So we have many kind of case study results where we've looked at, and right now we're thinking about that in nickel, which I didn't even get into, but we could talk all day about nickel. And maybe I'll just briefly say, I know this isn't a short answer, John, but what's happening in nickel right now is that there was a significant sort of perceived demand, prices going up, lots and lots of investment in Indonesia. Yeah. And where the kind of processing, because of the nature of it being coal-fired and the sort of island-based extraction processes, is very environmentally intensive. But now the prices have dropped, and Indonesia has a certain hold on the market that's then making it more difficult for the other kinds of extraction approaches that maybe have a lower environmental impact to play a role. And so that speaks to the challenge between supply and demand policies, and how those need to be communicated together at the same time. That this sort of supply gut from Indonesia led to this decreased prices, and the suppliers from outside of Indonesia are starting to need to shut down production. And that's just an example of the ways in which that mismatch causes challenge.
Absolutely. And the price volatility, I mean, it is remarkable if we look at the price of lithium just over the past 2 years, just to see that how much it's come down just recently, and then trying to understand where that might be going and the impact that has on industrial investment. It's really spectacular. Okay, Seamus Joyce Johnson had a question. How much opportunity is there to make the mining and processing of these materials less carbon intensive?
There is tremendous opportunity. We're engaged in an effort right now at MIT that we're calling Reimagining Resource Stewardship, with a set of mining companies to work on just that. But these are very big industries, very big capital. And so knowing as much as they can in how to make the right investments to do that as they can, is the significant opportunity there. And my, I don't know, overly jargony way of thinking about it is, what does the laparoscopic surgery of mining look like, right? So how can we think about, the mine that it's, because a lot of times you hear about zero waste mining, where we're lowering tailings. That's all really important, but what is the mining that leaves no footprint? And how do we think about the right sets of simulations, the right sets of precision technologies in order to really do that? So that's the blue sky. That's where we need to be thinking and reimagining. There's lots of I don't know, low-hanging fruit's probably not the right word, nearer term opportunities in terms of making better use of tailings, of those I showed on that cobalt pile. The activity at the mine itself, in terms of the, to come back to mobility, to, thinking about the trucks that are used and electrifying that, and the energy sources at the mine. But there's really strong need for really transformative thinking in that space. Yes.
Maybe just a super quick follow-up. I mean, I only recently learned the word tailings, mining waste. You showed that tailings volumes are increasing for many materials. Why is that happening? Like, why is the proportion of tailings increasing in the mining industry?
The ore grade is going down.
Okay.
As we need to dig up more rock per ton of copper that we're able to obtain. And there's the opportunity of tailings is big. So if you have a good idea in tailings, get on it, because there's a vast amount of historic tailings, but then there's current tailings, but then also the ability to extract with less tailing. So that there's opportunities in each of those pieces.
Super. That's clear. Webb Faribault had a question. Should the financial, social, and environmental costs of materials needed for batteries lead us to rethink the EV transition as a priority?
No. We have to decarbonize. We have to think about all the different ways in which we might do that. The way I think about it is that, we have to take decarbonization as the given, but then think about what the implications of that are and manage those as effectively as it can, simultaneous with looking at other ways of decarbonizing. To me, it's difficult to imagine a world that doesn't need all of the things that are good ideas. And so I don't mean to overly, have a reductionist approach to the question, but I really do think it's about thinking about the recycling infrastructure. How do we design policy that means that, we invest in recycling, even though it isn't relevant for the next X years, but in order for that to make sense, we need to be thinking about the pack design. So it's a little bit about prioritizing that. But that is definitely needs to be something we do. And so then it's about managing the implications of that.
Excellent. Daniel Frere had a question about the decrease in mineral content in traditional mines. Does that open up the opportunity for ocean mining or even asteroid mining? Any reflections on sort of expanding the scope of mining?
Yeah, I don't have a lot of thoughts on space, but there are lots of people on campus that like to talk about space. So we'll have to take space for another session. But we do have some work we think about in the sea. And this work has been led by Rich Roth and Randy Cochane, who I mentioned Rich at the beginning through the Material Systems Lab, but also Tom Peacock, who's in mechanical engineering at MIT. And they're, significant environmental implications that need to be thought through very carefully. There is lots of discussion about sea mining and how that might play a role along similar sorts of time trajectories as we would think about recycling, right? So it's sort of not, these are longer term questions that we need to be thinking about and thinking very seriously about the environmental implications associated with it. Right. But not as a significant part of the pie relative to the problems we've been talking about today.
Yeah, I mean, this concept was reflected in quite a few of the comments in the chat as well, which is just, sort of the big question of how do we avoid solving one problem, which is climate change, by creating a new problem, which would be, wastewater into our groundwater contamination, destruction of the environment, and other capacities.
Yeah, and so that is 100% the right question. And so and I do think it is something that can be done. And maybe, I am an optimist. And I've talked about this in a couple of different ways around, the policy that thinks about supply and demand linked. But let me see if I can break this down a little bit. We try to think about, so if I'm thinking about what does sustainable supply look like, that includes things like strengthening sustainable demand within the value chains of interest. So let's say battery value chain, because we're thinking about that now. So there'd be the sets of markets and policies that would help that, like IRA, but then it's also filling in knowledge gaps associated with that. Like, what is green? What is going to be a differentiable and discernible market? How do we think about that quantitatively? So, that's on the kind of demand side. And then if we think about sustainable sourcing, and that, sustainable sourcing of minerals, but then how that translates to sustainable production. There are ways that we've thought about thinking about what are called battery passports. So the kind of traceability and data associated with batteries as a way to engage communities. And then the policies that would help demarcate that on a supply chain supply curve, as we call them, right, in the analytical sense, but kind of within what sorts of signals should that send, and then there's a sets of knowledge gaps around that, and then finally building capacity for sustainable production. And here the case of nickel in Indonesia is kind of moved directionally the wrong way. But how can we think about vertical integration to think about supply chain sustainability and resilience, financing mechanisms for mining projects that are going to decrease the risk of investment or decrease risk, of investment in sustainable supply pathways. So like that we're putting that on the level playing field with the lower cost, higher environmental footprint. Here, there's knowledge gaps around what does that innovation need to look like. So that was a long answer to your question, but it's a fairly big question. But I do think it's possible, and it's about the sort of policy, knowledge, and market signals that would get at demand sustainable demand strengthening, sustainable production strengthening, and extraction.
Maybe just to quickly double click on battery passport, because I think that's probably a good example. Maybe just could you explain in like 20 seconds what is this battery passport? I understand it's been put forward in Europe, it's moved forward. Is it a good idea? What do you think?
I think that the dialogue so it's about tracking what the traceability, I guess, and to the degree to which we can associate data with these products. So I think it is a good idea. There's lots that needs to be understood in terms of how data would be collected, marked, the proprietary nature of it. But even having the conversation then forces the kind of standardization that I was talking about when I was talking about the sea that is a battery space right now. And that I think are the kind of more immediate benefits of such things. Super.
Quick question about the rise in LFP, lithium iron, IRON batteries. It's very confusing versus ION batteries. The rise of LFP batteries making cobalt use less in demand. Do you sort of see that as a dominant trend?
Yeah, and I had too many thoughts such that I didn't mention this one. But another thing on the demand side that has happened recently that I like is like thoughtful demand, so to speak, of like using the right material for the right application. So I'm glad that you asked that question, because I glossed over that. So LFP used to be something we talked about. We stopped talking about it as we were demanding high energy capacity, energy density, power density, but in the right applications as we're trying to electrify. And maybe that sort of gets back to this overall question you asked about electrification. Like, let's use the right technology in the right place, given what the demands are, the property demands. And that has been challenging before because we weren't thinking about it as ubiquitously, maybe is a way to think about that. But now there is and there's also been improvements in the technology, of course, because of awesome material scientists. But then also just finding the right market given the properties of the product.
Elsa, we have so many more questions. We're out of time. I'm going to turn it back to Jinhua, but thank you so much.
Great. Thank you, John and Elsa. So one thing I learned is that the abundance per se is not the problem. It's the process of the distribution that's the problem. It's the environmental economic analysis, the consequence of that problem. So Elsa, we feel so fortunate for you to join us and share with your thought on this. Many questions, I think we should continue. Probably will invite you for round 2 to discuss many other questions on the way. So everyone, please join me. Thank Professor Elsa Olivetti for the presentation and conversation today.